All right, hello, welcome to Quantum Field Theory, week 15. Today we'll be talking about one aspect of high energy physics that has had dramatic consequences at the frontier of research. So I will sort of preface this by saying the following. By now, you should probably have the inkling that if someone asked you at the dinner table, if someone asked you the following question, if they said to you, give me one word, just give me one word that tells me the most important thing to a theoretical physicist, hopefully that word should be very apparent to you, that word should be symmetry. Okay, symmetry sort of defines everything about our theory. It kind of gives us some motivation. And, it didn't really have to work like that. It happens to be a powerful demand. It happens to be a powerful demand on the construction of any theory. No more. I mean, this is very, very explicitly seen in gauge theory, Yang-Mills theory, right? The whole theory that defines the standard model is defined on gauge symmetry, local gauge invariance. This is a deep principle that somehow gives us the standard model. So today we're going to look at one more kind of deep symmetry called conformal symmetry. And we're going to explore how we can exploit this symmetry to hopefully describe some physics, some new physics. Okay. And so that's the goal. I'm going to give you a brief introduction to conformal field theory. Next week, I'm going to give you a talk on non-abelian gauge theory or Yang-Mills theory. They're interchangeable because I feel like we need a formal talk on that. I kind of let you guys go on your own and look into that, but I think it's so important that I will also be talking about the beta function and the renormalization group. So that's my plan for next week, because I think we need some formal discussion of that versus, okay. And eventually that will lead us into a discussion on QCD. So that's next week. QCD, the beta function, Yang-Mills theory in general, touching upon all of those things. So what is a conformal field theory? So conformal field theories are quite interesting, okay, because they are exactly solvable quantum field theories. That's what's very interesting about them. As we know, quantum field theories are not exactly solvable, right? We're working in perturbation theory. We're using various approximation schemes to get an answer. Conformal field theories are exactly solvable to all orders. What is a conformal transformation? Okay, so we ought to define that. So let's say we have some sigma alpha going to some sigma tilde of alpha of sigma, some new object. And so a conformal transformation amounts basically to a scale transformation, as we kind of know. So if I have the metric G alpha beta, it becomes now scaled up by some factor omega G alpha beta. Okay. Well, I should actually be explicit with this dependence that I wrote down. So then I would have like G alpha beta of sigma goes to omega squared G alpha beta of sigma. Okay. So that is the crux of conformal symmetry. So a conformal transformation is a scale invariant one. Okay, that's the main idea. And so what is one kind of transformation you can think of that's scale invariant? Well, the simplest one is a dilation, right? Conformal symmetries preserve angles. That's the key. And so one transformation that preserves the angles, because preserving the angles of an object means you're preserving its scale. So let's say I have a circle, I dilate it out, right? The angle on that circle will stay the same. So that is a conformal symmetry. That's the most basic example of this. However, now we have dynamical variables that we can't talk about with conformal invariance. Can anyone think of a dynamical quantity that is not scale invariant? It begins with an M. E equals mc squared. What does the M stand for?
Mass.
Mass, right? So mass is not scale invariant. Exactly. So now if I blow up that circle, the mass has changed, right? It's a bigger circle. Okay, if we think that that circle is some blob with mass. Okay, wavelength is not scale invariant. Okay, so now we can't talk about massive excitations. That's the very first takeaway we should have if we want conformal symmetry. And so the language of particles and S matrices and Wick contractions and all of this gets thrown out the window. That's not how we talk about interactions now. And if we want a theory that's conformal, maintains conformal invariance, now we move to the language of objects called correlation functions, not to be confused with the ones in Q of T, and operators. So the language will be a little different. Okay. And these operators, we want to see their behavior under conformal transformations. I mean, this is a very vague, I literally just wrote, this could be any scaling. It's a very arbitrary symmetry. Okay, so we're going to work in, what I'm about to show you is doesn't seem very well motivated, but you're going to see why. So we're going to work in Euclidean, in complex coordinates. Okay, that's how we're going to define objects in this conformal field theory. That turns out to be a very useful mnemonic, or a very useful coordinate system to work in. So let's just spend a few minutes defining some coordinates. Okay, now, and right now we'll work in a Euclidean signature. So no minus in there, okay? Just Euclidean, all positive spatial dimensions. I haven't introduced a metric. I haven't talked about anything like that. So let's define the coordinates sigma 1, sigma 2. Oh, before we continue, let me give you the homework. Okay, so the homework this week . Let's see, what do I want to give you as homework? Right, the homework this week is chapter 3 in LDAN. It's just some reading, no problems this week. So chapter 3 in scattering amplitudes, chapter 50 in Strudnicki. I think that might be in spinor helicity. Chapter 27 in Schwartz. Okay, and extra, if you want some extra. Chapter 2 in Polchinski's string theory. I give you fair warning. So chapter 2 in Polchinski's on CFT. Okay, I give you fair warning that this is a very difficult book. Okay, so just, if you want to look at it, look at it. There might be a lot of things in here that you don't get. That's okay. I certainly did not understand Polchinski the first read. I had to really read it a few times, look at different sources. It's a difficult book, but this is sort of the best source for this at a more technical level than what we're doing here. Okay, so that's the reading. Okay, anyway, so we have a coordinate sigma 1, sigma 2. And we're going to write these now in some complex coordinates. So this will stay sigma 1, this will become I sigma 2. Okay, that's the first step. And we're going to define two coordinates, z and z bar. You might have seen this if you're very familiar with complex analysis because they come up all the time. They're just some complex coordinates. So this one will be sigma 1 plus I sigma 2. So they're complex coordinates. They have a real part and an imaginary part. Let me erase this. Okay. And then z bar is just defined as sigma 1 minus I sigma 2. So this is how I'm going to define objects, by these complex coordinates in the plane. Okay. And so there's two kinds of functions in complex analysis: holomorphic functions and anti-holomorphic functions. So holomorphic functions are sometimes referred to as left-moving functions. Anti-holomorphic functions are sometimes referred to as right-moving functions. So this would be a holomorphic function. This would be an anti-holomorphic function. But then you say, okay, what's a holomorphic function in the first place? Basically, it's actually a very jargony mathematical word. All a holomorphic function refers to, we kind of discussed this, is a continuous function in complex plane. That's all it is. Anti-holomorphic is just in the opposite side of the plane. It's like you flipped all the points around. That's basically in effect what this minus sign is doing. Just flipping all the coordinates around, and now you have two sides of the plane. So it turns out in complex analysis, actually having a function that's continuous on both sides of the plane is very difficult. Okay, so if you go on Google and you type in the words analytic continuation, you'll see you actually can't continue a complex function around the plane. It's not possible, right? So if you just think about the complex plane for a little bit, you can't continue the function around the plane. You have to have two specific regions you define, two boundaries. So it's a little complicated, but take my word for it that these are the two coordinates we're mapping. It's kind of like a map on both sides. Okay, so those are our coordinates. Now we can define derivatives, right, with these coordinates. So these are the derivatives. If you've ever seen any of the work I'm doing or a calculation, you see these z and z bar derivatives all over the place because that's the little place we're working in. So let's define dz. So these are the holomorphic derivatives. So dz is just defined as, so we'll sometimes just write it as d or del, right? Just as a shorthand. And this is just defined as 1/2 d1 minus I d2. Okay, so that's the holomorphic derivative. And the anti-holomorphic derivative, dz bar, sometimes we just write as d with a bar on top, and we can write that as 1/2 d1 plus I d2. Okay. Where these relations dz equals d bar, z bar equals 1, right? So these relations hold, and d bar z equals d z bar equals 0. Okay, which is just obvious from the labeling of the variables. Okay, so now the metric, so flat Euclidean space now in these coordinates looks like this: ds squared equals d sigma 1 squared plus d sigma 2 squared. Okay, so that's how I write the flat metric. Or in more suggestive coordinates, I just write this as dz bar. That's the metric. This is flat Euclidean space in this nice dz bar coordinate system. Okay, and now the metric, sorry, this is the line element, right? ds squared. I keep calling the line element the metric, but don't get confused by that. Now this is the metric. So gz equals gz bar equals 0. Now this is the real metric that we usually refer to. Okay. And the metric is symmetric. So gz z bar equals gz bar z equals 1/2. Okay, that's the metric for flat Euclidean space in this conformal thing. And you can work out pretty easily that dz bar equals 2 d sigma 1 d sigma 2. Okay. Okay, so if we want to write down like a Dirac delta function in this z bar coordinate, we would just have the integral d2z delta z bar, and we just get the standard relation that integral equals 1, right? We have done nothing fancy here. All we've done is define new coordinates they're in some sense a two-dimensional coordinate, right? Z bar. That's all we've done to define the holomorphic and anti-holomorphic parts of our function. This is nothing really spectacular. Okay. So, with any coordinate system, you have to just think about it a little bit and it should be clear. Okay, let's define vectors in the space. Okay, so if I have a vector v, vz is equal to the following. So vz would equal v1 plus I v2. Okay, that's a vector. Okay. Vz bar, you probably guessed it, equals v1 minus I v2. I'm just defining the coordinates of vectors now. Vz lower equals just 1/2 v1 minus I v2. Okay. Of course, we can lower the indices with the metric, right? So this is going to require the metric. That's why you get this factor of the 1/2. Okay. And Vz bar equals 1/2 v1 plus I v2, right? Because now if I want to lower, I need the metric gzz bar equals gz bar z equals 1/2. Okay, so that's why we get these crazy, but believe me, the factors of 1/2 all cancel when you do calculations. They don't really stick around. Okay, any questions? Those are our coordinates that we work with for this conformal field theory. It turns out to be a nice coordinate system to work in. Okay, let's continue then. So let's just talk a little bit about the semantics of the metric. So you can have dynamical metrics. So far in relativity and quantum field theory and all of these kinds of things, we've been working with fixed background metrics, right? I define the Minkowski metric, G or eta, whatever you want to call it, and it stays fixed. That's fine. You can have a fixed metric, no problem. Okay. And if you work with a fixed metric, right, if the metric doesn't change, right, but I've never shown you a metric that's dynamical. All right, the metric is sort of this fixed quantity. There's no rule that says you can't have a dynamical metric. I just want to make that clear. If you have a fixed metric implies global symmetries, right? That's where Noether's theorem comes from, conserved currents, all of these kinds of nice ideas actually stem from the fact that you do have a fixed metric. Okay. That's not to say you can't have global symmetries with the dynamical metric, but the nice global symmetries we talk about in quantum field theory partially have to do with the fact that we have a fixed background metric or a fixed background topology we're working with. Okay, in string theory, we're not going to do string theory here, but I just thought I'd mention it. You actually have a dynamical metric. You start with a dynamical metric. Okay. And all of the transformations of the metric are just pure gauge. They're just residual gauge transformations that leave the metric invariant, right? They're just gauge transformations that can be undone by some wild transformation. Okay. So you can have it. We're going to do fixed metrics because we're not doing string theory here, but I just thought I'd mention that as a slight technical point. Okay, so let's say we have Z and we want to now have some conformal transformation on Z. So let's say Z prime equals now F of Z. Okay, some conformal transformation. And similarly, we'll have Z bar go to Z bar prime equals some F Z bar, some conformal transformation. We'll just put a bar up here too, F bar of Z bar. So it's very explicit. And so my metric, my line element, sorry, ds squared equals dz bar. now goes to the following. Now it goes to something like, I guess, I don't know, df dz squared, dz dz bar, right? Now it's just scaled by this conformal transformation. So we're going to study a specific case of conformal field theory. It turns out to be actually the most useful case, okay? And that is 2D conformal field theory. No one really uses higher dimensional conformal field theories in practice. And I could go into a long technical discussion of this, but I won't. So I will just sort of tell you why 2D conformal field theory is so useful, both in a kind of a vague sense, which might not be as helpful to you, and in a bit more of a technical sense. First thing, in 2D conformal theory, conformal field theory, we have an infinite number of transformations, okay? Second point, you can build all higher point discussions of dynamics in 2D conformal field theory from a simple 3-point function. It actually turns out to be a very nice, simple theory to work with. Third point, 2D conformal field theory is sort of the best way we know to describe a lot of aspects of quantum gravity, for example, right? With this flat holography we've been talking about. Happens to work out nicely in 2D. Okay, so there's technical reasons why as well we use 2D conformal field theory over higher dimensional conformal field theories. I won't really go into that. But one thing you should also consider is the group theory structure of all of this. So the global conformal group, SL2C, is a 2-dimensional group, right? So all of the global symmetries come into this 2-dimensional group, SL2C. I'll write that down. So the global symmetry group we're working with here is SL2C. And in fact, Johnson's going to show you that this is isomorphic to the Lorentz group, which is a big deal for us because, so this is isomorphic to SO31. Okay. So anyways, now that we're got that out of the way, let's write down some conformal transformations. So the most obvious one, I can have a translation. So Z can go to some Z plus A. That would be a translation, where A is some translation vector. I can have a rotation. So Z goes to some zeta Z, zeta some rotation, I don't know, where the magnitude of zeta is going to be 1. Okay. So if zeta equals 1, this is a rotation, right? But if zeta does not equal 1, well, then this is a dilation. I'll write that down. So rotation. Dilation. These are all conformal symmetries, right? This is a translation. That's the most trivial one. Okay, now we've been working in R2. Now we're going to move to C2, right? We're working in some complex coordinate system. Okay. Okay, so now we set all of that down. Now let's describe some of the basic objects that we've worked with so far. We'll begin with the stress energy tensor. Now, we'll do this, we'll describe classical aspects first of this theory. We're not going to talk about anything quantum yet. Let's just talk about classical aspects of all of this. So in classical field theory, the stress energy, well, in quantum field theory and classical field theory, the stress energy tensor is very important because the stress energy tensor is sort of the matrix that stores all of the conserved currents of the theory, right? Right? So we derived some Noether currents, right? You can do this in classical field theory or quantum field theory, it does not matter. You derive some conserved currents, and then you store them in some matrix, and we call that matrix energy, the energy momentum tensor. Sorry, in GR, it's also called the stress energy tensor, but that's a totally different thing that has physical properties like pressure and energy density. So this is a different object. This is what we call the energy momentum tensor, and it stores conserved currents. Okay. So let's say we have some translational invariance. So let's say delta sigma alpha. Sigma alpha is now just some vector, 4 vector in this coordinate system, now equals some epsilon alpha. So it has some translation invariance. And let's also say that we're in just flat space. So G alpha beta equals eta alpha beta. By the way, these are my notes. So if you find errors, let me know, okay? These are kind of taken from a mishmash of things. Okay, so now let's derive some conserved currents. Okay, I see, this is the thing. Well, no, never mind. So how did we do this in standard quantum field theory? All right, so now what do we want to do? Let me just be clear. We want to derive conserved currents in this new conformal field theory space, okay? And how are we going to do that? Well, we're going to have some action, and we're going to vary that action, and from that will fall the conserved current, right? Just like we did in standard QFT. So let's say we have the action S, and I'm going to vary some action, and that's just the integral of some d2 sigma, right? Because now we're in this 2-dimensional space. This is a 2D conformal field theory, right? And we're going to have some J alpha del alpha, right? This is our famous conserved current equation, right? Times epsilon. Okay, that's the variation of sigma. So this is just delta sigma alpha, right? So another way I could have written this variation, delta S, is the integral of d2 sigma J alpha del alpha, variation of the 4 vector delta sigma alpha, or not the 4 vector, the 2 vector. We're in a 2D space now. I keep calling it a 4 vector, it's not. Okay, of course, just standard variational techniques, delta S must be 0, right? Hopefully that's very straightforward for you guys at this point. And so that means that J alpha del alpha must equal 0, right? Because this variation can be anything. It can be any delta sigma alpha or epsilon. Okay, and now, of course, we should also recall, this looks very familiar to standard QFT, where J alpha is just some conserved current. Or conserved nodal current, if you want to label it that way. Okay, so this is a very simple, very little 2-line discussion about what we talked about in QFT in some depth. Okay, let me erase the board. So basically all we're doing now is recasting the theory in this 2-dimensional space, and we're demanding that this 2-dimensional space has conformal invariance. Now, there's a name for this 2-dimensional space that people use, is particularly in string theory, called a world sheet. So instead of a world line in standard SR, where you have one coordinate that defines a trajectory through space-time, now we have 2 coordinates that are spatial in nature, sigma 1 and sigma 2, that define my position, or z and z bar, that define my position in this 2-dimensional complex space, and we call that space a world sheet sometimes. So I might use that phrase. It just depends on my mood. Okay, let's continue. So now let's consider a dynamical background metric. So let's consider dynamical G alpha beta. So now let's promote G alpha beta as a function of sigma. So now it's dynamical. Okay, so now it depends on sigma. Okay, then delta sigma alpha is going to go to epsilon alpha of sigma. Now epsilon is now a function of sigma. Some diffeomorphism of sigma, now it's a function of sigma. And delta G alpha beta is going to equal del alpha epsilon beta plus del beta epsilon alpha. Okay, so that's the variation of the metric. And so now my variation of the action is not as simple, because now it's going to depend on derivatives of this guy. Because now this is a function that's dependent on sigma. It's not just a fixed quantity. Okay. So now the variation of the action, I'm going to need a minus sign is the integral d2 sigma. That's fine. That's just our integration variable. But now I'm going to have some del S, del G alpha beta. This should look kind of familiar to you. I'll explain it in a second. Delta G alpha beta, right? Just the variation of the metric. Okay, a few comments on this expression now. First comment is this is basically a functional derivative. It's not a standard derivative. S is just some action. And G alpha beta is a functional, right? It's a function already. You're taking the derivative of the function. It's a functional derivative. Okay, that's the first comment out of the way. Second comment to make here is now that this variation of the action, the reason we need to add this derivative in here is because it's a dynamical quantity. Okay, that's something important to think about. Okay. So now I'm going to use some of the identities we just wrote, and now I can just rewrite this as minus, let me make sure I get this right. Minus 2 d2 sigma ds dg alpha beta d alpha epsilon beta, right? Just bring in that minus 2, I can multiply it and get this expression out for delta G alpha beta. Okay, that was a trick, kind of a simple thing. Okay. And so now we have our conserved current from translational invariance. Okay, we've put some conformal transformation, except now it's dynamical. Except now the energy momentum tensor is going to take some weird form. So let's write T alpha beta. Right before T alpha beta was very simple. Right before T alpha beta, so let's just write T alpha beta. So before, I'll put a bullet here. Before T alpha beta was just J alpha D alpha. All right, all of the currents, and these were just conserved. Same thing, this is also going to be conserved, but now it's going to be some more complicated object because we made the metric dynamical. Also, don't worry too much about this. We're never going to deal with them. I just want to show you how it looks like. You're going to like this a lot because this is just going to be, you can work this out, minus 4 pi over the square root of the determinant of the metric. ds dg alpha beta, and your radar should be going on because this is pretty much identical to the expression of stress energy from GR. Okay, not that it matters really, but the form, the mathematical form is the same. That's because in GR, you can have a dynamical metric if you'd like. Okay. And so when you're deriving the Einstein equations, we did it with an action in the vacuum. When you're deriving it with a source, i.e. T mu nu, you get this form. So if you look at Carroll, you get this form for stress energy. So my suggestion to you is to go in there, look at how Carroll gets this expression, and look at the analog between that and this. They're very similar. So it's important to keep straight in your head the difference between a dynamical metric and a fixed background metric. Fortunately, we don't have to worry so much about all of that in our context. So in flat space, G alpha beta is just delta alpha beta. Remember, we're working in some Euclidean space right now, so we don't have a minus sign. And in flat space, then D alpha T alpha beta must be 0, right? This is conserved, and so this divergence must be 0. If I'm in curved space-time, well, then this is just covariantly conserved. So this is just nabla alpha T alpha beta equals 0. So now I'm just in, now it's just covariantly conserved in curved space. a very simple extension. And so that's our stress energy tensor, energy momentum tensor, sorry. These names are interchangeable, but sometimes it's better to use the right jargon. Okay. Okay, another very nice thing to note in these conformal field theories is that the energy momentum tensor is traceless. So let's say we have some variation of the metric, so some delta G alpha beta, which I now define as epsilon G alpha beta. Okay. Then as we've just described, the variation of the metric delta S is just the same expression we've been writing down. It's just the integral d2 sigma del S del G alpha beta delta G alpha beta. It's the variation of the action. And just using all of the machinery we've been writing down, now we can just write this as -1/4 pi integral d2 sigma square root of G T alpha alpha. Oh, I need an epsilon. Okay. You can work that out just from all of this, all of these expressions we've written down. Okay, so this is very nice. Of course, epsilon and G can be any non-zero quantity. We demand that delta S is 0. Therefore, T alpha alpha, or the trace of the energy momentum tensor, must be 0. Okay, so it's traceless. This is just the trace, right? T alpha alpha. Okay, this only holds in flat space. This only holds in flat space. And this is all classical. It turns out when we do some quantum magic, this becomes a very hard condition to hold. And if we just step back and think for a second, why is this the case? I'm not going to dive into it. I'll let you think about it and we can discuss it. You will find that this idea that this energy momentum tensor is traceless comes from the fact that we want scale invariance. Scale invariance demands this. This is a hard condition to meet in the quantum theory because we have masses and all of these crazy things, but we'll deal with it. Okay, excellent. So nothing insane so far. We've kind of just been recasting things we've already done in quantum field theory. We've done all of these things in quantum field theory. But this is a little new because we've always had a fixed background metric, i.e. Minkowski. You can look back, I think, to lecture 3, 2, 3, or 4 has our discussion of symmetries. That has the whole derivation I did of Noether currents and the energy momentum tensor. Okay. In standard quantum field theory. Okay. You can remember that depended on our Lagrangian, right? We had a Lagrangian, and the action is technically the Lagrangian, right? S is just the integral of the Lagrangian. So all of these things are just Lagrangians, right? At the end of the day, they're just expressions of energy. Okay. Okay, let's keep going. So what have we figured out? So remember, Z is a coordinate that goes sigma 1 plus I sigma 2. Okay, we figured out that the energy momentum tensor is traceless. Okay, that just comes from basic variational principles, which if we want to write in our nice little coordinates, Tz Z bar is just 0. That's the same thing as saying that. We've also figured out that conserved currents imply the following in flat space, that the divergence of the energy momentum tensor must be 0. Which again, if we want to cast this in our new coordinates, we can write this as just del t z equals 0, and del bar t z bar equals 0. Okay. So let's talk about no-other currents now. Let's derive some conserved currents. All we've done so far is derive the fact that our currents must be conserved. But I haven't actually told you what those conserved currents are. Okay, right? The divergence of J just tells me that the current must be conserved, but the conserved current could have a variety of forms in itself. J is the conserved current. Okay, so let's talk about that. So of course, T alpha beta yields no other currents. That's the big idea for translations, right? So what are the currents for the other conformal transformations? So far we just had some epsilon, that's the translation, and that yields no other currents. But what about for dilations and rotations? Must have a different form. So let's talk about that. So let's say we have some dilation. So let's say Z prime equals Z plus epsilon Z. Again, epsilon is now some function of Z. And let's say we have some Z bar prime equals Z bar plus epsilon Z bar of Z bar. And we'll put a bar above the epsilon, make it very explicit. Where, it's important to remember that really when I'm writing epsilon of Z or epsilon of Z bar, I'm really implying that these are functions of both Z and Z bar. It's just one is 0. So again, we have a dynamical metric. So let's write down the variation of the action. Same idea. So delta S. I'll give you a second to think about it. So this is just our standard minus integral d2 sigma del S del G alpha beta, right? This is just our dynamical action or variation of the action, delta G alpha beta, right? What we've been writing down. Okay. Let's implement these transformations. So if I do a little bit of algebra, I get 1 over 2 pi integral d2 sigma T alpha beta. Let me just make sure. T alpha beta. Right. Del alpha delta sigma beta. Okay. Coming from the variation. And now I want to write this in Z and Z bar coordinates. Now I'm going to get that little expansion guy. So this is just going to be 1 over 2 pi again. Integral d2 sigma, not d2 sigma now. Now I want Z and Z bar coordinates, right? So that's going to change. So d2z, that's my new integration measure. And so now I can define the stress energy tensor in this new space. Okay. That's just 1/2 times tzz. Okay, I just want to think about this for a second. tzz. Right. I got it. tzz del z delta z. Just want to make sure I'm doing this right. Yes. Plus t z bar del z bar delta z bar. Okay, and that is the stress energy tensor now in this nice little coordinate thing. And I can rewrite this even more. So let's just do some more algebra. So 1 over 2 pi integral. D2Z, DZZ, DZ bar epsilon, plus T, Z bar Z bar, DZ epsilon. Yeah, okay, that's my final expression in this coordinate system. Oh, sorry, wait, do I want a bar? Let me think. DZ bar epsilon. DZ, yeah, this needs a bar. Damn, epsilon bar. Okay, again, delta S is 0. Therefore, conformal symmetry demands, I'll write it here, that T Z bar equals T Z Z equals 0. Or actually, rather, one or the other must be 0. It depends on what you're interested in looking at. Right? If the conformal transformation is acting on the bar coordinates, well, then Z bar is 0. If the conformal transformation is acting on Z, well, then TZZ is 0. It depends on what it's acting on. Okay, so basically, the big takeaway now, just a side takeaway, despite all this, is that Z and Z bar, you can treat them independently. They're really independent coordinates, right? That's an important thing to conceptualize, that you can treat them independently. Part of that has to do with the analytic structure of all of this whole holomorphic, anti-holomorphic idea, not idea, but construction, really. And part of this has to do with the fact that it depends on what the conformal transformation is acting on. Okay, so this is kind of a misleading expression, but I think based on what I said, you can decipher it. Okay, let's work out some more machinery. I'll be right back. Oh, there's some streaks on the board. I don't know how this happened. Maybe my eraser was a little wet. Okay, it's okay. Okay, let's treat Z and Z bar now as independent coordinates. That's what I was getting to. Okay, so let's define the following. So let's say I have some delta Z, some variation of Z, and we'll call it epsilon of Z. And let's say now my variation of Z bar is 0. There is no variation of Z bar. Okay. Therefore, now epsilon goes to some epsilon of Z times F bar of Z bar. Just some unchanging function of Z bar. Okay, and let me just write down this expression here. So the final expression we derived was 1 over 2 pi integral. I'm just writing down the final expression for the stress energy tensor that we derived. So it's D2Z, TZZ, DZ bar epsilon, plus T Z bar Z bar, DZ epsilon bar. Okay. Okay, so now based on this conception, that means that JZ must be 0. I have a conserved current. That's obvious. Okay, and that means that JZ bar, because remember, the dependencies are flip-flopped. The DZ derivative depends on TZ bar Z bar. The DZ bar derivative depends on TZZ. So this will be non-zero. Okay. So this is just going to be TZZ of Z, epsilon of Z. Let me get all that junk now. Which in shorthand, I can just, write as T of Z, epsilon of Z. I can drop those little indices. We do that all the time. So I'll just make that clear here. Right, and now we can just write everything out. So del alpha J alpha equals del Z JZ plus del Z bar JZ bar. We're treating them independently equals 0. So now our conserved current equation just treated independently. Okay. And so that's the basic idea now. I can do the same for Z bar, right? So delta Z bar just equals epsilon bar of Z bar, right? And just do the same thing. Delta Z equals 0. Right now I've just changed the transformation. That's all I've done. And then we get the following, right? Now we're going to get a little bit of this thing flipped up. So now J of Z is going to be non-zero instead of J of Z bar. And now this J of Z is, JZ is going to have some Z bar dependence, right? So now this is just T bar epsilon, no, sorry, T bar Z bar epsilon bar, okay, of Z bar. Okay, and then you guessed it, JZ bar is 0. I just flipped it around now. And that has to do with the fact that these derivatives are all mishmash. Okay, so I just showed you the other case quickly. This is just to say that now I can treat these things as independent coordinates and get a conserved energy momentum tensor for either or, depending on what I want the conformal symmetry to act on. Right, because now this, what we derived, if you get nothing out of this, we derived some expression for the energy momentum tensor. Okay. And we've shown, and we have discussed now, how this expression for the energy momentum tensor truly is independent of Z or Z bar, truly is independent of our coordinate. And we can act that conformal symmetry on either coordinate. That's an important idea. In fact, in the paper I'm writing now that I sent you the draft of, the symmetry acts on Z bar. That's where the important symmetry is, the sub-leading soft graviton theorem, sub-leading soft graviton theorem. Acting the symmetry on Z would give you something very trivial and silly. So oftentimes this, we take this for granted. This is just to show you that you can act on things depending on the coordinate of interest. Okay, let's do a little example of all of this. Okay, let's do a nice example that hopefully will clear this up a little bit. So let's just do the example of a free scalar field. So no interactions, classical. Let's do a free classical scalar field. Okay, and let's write down the energy momentum tensor. That's the goal. So let me write down an action. So S equals 1 over 4 pi. We'll call this some coupling alpha prime. Or not a coupling, some arbitrary scale dimension, no interactions. Integral d2 sigma, d sigma x, d sigma x, where x are just some coordinate positions in this space. Or actually, let me not call these sigma, because x is dependent on sigma. So this is alpha. This is alpha, right? Where x is now just some function sigma 1. 2. Or let me write this better. So x is defined now as some function of sigma 1 and sigma 2. That's why I shouldn't call those sigma, I should call those derivatives alpha. Okay, so is the free scalar field conformal? In other words, can I let sigma alpha now go to some scaling lambda sigma alpha, where lambda is some scaling object? The answer is yes. So how would we do this? So now x of sigma, okay, is going to go to what? It's going to go to x lambda minus 1 of sigma, for example. We can just scale each coordinate. Similarly, the x of sigma. So this derivative is going to come up in the action, right? D sigma alpha. This is going to come up in the action. And if I scale it, well, then I just get this. So del x lambda minus 1 sigma over del sigma alpha, right? I just scaled each coordinate. And so we can write this down as now 1 over lambda dx, we'll call it sigma tilde, the scaled coordinates, d sigma alpha. Okay. Or you know what, we'll call this sigma tilde, just to hammer in that this is the scaled coordinates now. That's kind of better notation. And we'll define sigma tilde as just lambda minus 1 sigma, which, as you all know, this is just 1 over lambda sigma. Okay, then our integration measure in the scaled thing becomes d2 sigma lambda squared, right? Now we have that scaling thing to worry about, d2 sigma tilde. Recall, sigma tilde is 1 over lambda sigma, so it gets rid of these lambdas. So the integration measure stays invariant based on our construction. Okay. So far, so good, right? This is kind of a little, very little simple canned example. Just with all the machinery we've been working with. So now let's write down the stress energy momentum tensor. You can find, and you should derive, that T alpha beta might give you it as a problem, is 1 over alpha prime. Yeah, we'll give you that as a problem to derive this. Shouldn't be too hard. Del alpha x, del beta x. Minus 1/2 delta alpha beta del x squared, Kronecker delta. And we have the standard traceless condition. So T alpha alpha equals T z bar z bar. Sorry, T z bar z. Those are the diagonals. Okay, so this is the full energy momentum tensor. Obviously now I can write this as z or z bar. There's pieces of z or z bar. So let's do that. It's kind of trivial, but I will pen it down so you guys have it. Okay, again, so the full energy momentum is just 1 over alpha prime. Okay, that's for a free scalar field. Okay, so T is just 1 over alpha prime del x del x. That's the z component. sorry, minus, you're gonna need a minus. And then T bar is minus 1 over alpha prime, V bar x, Q bar x. Okay. And you can derive an equation of motion, d bar x equals 0. This will be your equation of motion if you follow through the whole variation of the action. Where now I can write down x of z and z bar as x of z plus x bar z bar. Okay, now let's talk about the quantum theory. Okay, and we'll talk about probably the most important object. This was all classical. This was all kind of fine and dandy. We'll have you derive this expression up here as a problem. But now, once we work all of this out, this is all fine. It matches, it looks very familiar, right? Because in standard QFT, you get that T mu nu is equal to some derivative term minus the Lagrangian. So here we just have minus this Kronecker delta because of the way the metric works. So it looks kind of familiar. I would refer to those earlier lectures if you want some more background on this, because we went into this in a lot of depth. You might not remember it because it was at the very beginning of the course. Okay, but let's talk about the quantum theory now. Let's talk about a conformal field theory, okay, in the quantum sense. So one very important object in standard QFT is the operator product expansion, right? Or correlation functions, right? That's kind of like the main object we want to compute in standard quantum field theory, right? Correlation functions, 2-point, 3-point, higher points. And we found that the solution of those correlation functions are Green's functions, right? That's the whole, if someone asks you, what's the big idea, right, of basic field theory, you could probably write down some small correlation function and explain what you're trying to compute. This idea of the OPE, that's what I'm going to start calling the operator product expansion. This idea of the OPE really comes into its own in conformal field theory. It becomes a very interesting, unique object, and it's really the main object of study, honestly, or these OPEs. So let's discuss. So we have to ask ourselves the question now, right? Because if we want to write down an OPE, right, or a correlation function, we need to define what an operator is, right? And in standard quantum field theory, our operators were phi, right? Scalar field theory, the fields were phi, or spin 1/2, the fields were psi. We had fermion fields. That was the operator, right? You had field operators. You acted on them, or the field operators acted on each other, or the field operators acted on spinors or other states, and you derived amplitudes. That was the whole idea in perturbation theory. In conformal field theory, we don't really use the word phi, or the operators aren't really fields, okay, in the same way they are in quantum field theory. The word, the way we define a field in conformal field theory is kind of more loose. It's different than the phi you'd find in the action in quantum field theory. It's not the same phi as you'd find in some regular action. All the phis are any local. So let me write down. So first of all, what is phi? Now, phi is some object. It's an expression in each point in this space, right? Z and Z bar coordinates, right? That is, and each point defined in this space, Z and Z bar, is invariant under conformal transformations. Okay, it's not really a field, because a field is a function of what? Space and time, 3 + 1. This is different. We're not working in 3 + 1 here. We're working in 2 spatial dimensions, Z and Z bar, holomorphic and anti-holomorphic pieces. And so this phi is something that we demand is conformally invariant, that's defined at each point now in Z and Z bar, not X, Y, Z, and T in that non-Euclidean space. That's a very important distinction. That's why I wouldn't say it's the same phi as the phi in the action. So these are all local expressions in the sense that they all affect one another. Okay, they all kind of work together. If I put a bunch of these conformal, we'll call them conformal operators, they're all going to affect each other in the dynamics, depending on how I define them. That's quite different than standard quantum field theory, because standard quantum field theory, you could have two space-like separated phis or fields that don't affect each other. Okay, so basically the name of the game in conformal field theory, we're defining a space where all of these operators are in tandem with one another, playing off of one another based on some dynamical principle. That's quite distinct from standard QFT. So just we need to be very clear on that. So it could be any expression in CFT. I could have some derivatives of phi defined at each point. Right? That could be one option. I could have phi defined as some phase. So I could have some e to the I phi at each point in this Z and Z bar space, and so on and so forth. So here's the thing now. Let's say I have some bunch of operators doing all kinds of dynamical stuff. That's the name of the game. What the operator product expansion tells us, and now look, okay, let's really break this down now. Let's just say I have some dynamical space. Yeah, I have some dynamical space that I want to do physics on. Okay, and I have a bunch of operators. So I have a point here, I have a point here, I have a point here. Will not make this too big. I need room to draw, to write all the equations. What we say in conformal field theory, what we can do. First of all, we are interested in the point where these two operators are very close together. We'll call this O2 of Z. We'll call this O1 of Z. And what we say is we can write down an OPE based on three operators. We have two going into one, because now these 2 points are coming together. And what the OPE tells us is we can build off all the dynamics of everything going on by looking at the point where these two things come together. In other words, the formal statement. Two local operators, this is what I wrote down, two local operators inserted at nearby points can be approximated by a string of operators at one of these points. Okay. So the name of the game in conformal field theory is to talk about this area where these 2 points are coming together and describing the dynamics, and from that we can build up all the dynamics. Or actually not even that. This is really what's interesting. Okay, when these two operators are coming together. So OI, we'll call OI the set of all local operators. You'll see what I mean by this in a second. We need some more equations. And so let me write down the definition of the OPE first, then this will give you a better sense. So we have some OI, function of Z and Z bar, OJ. Right, this is kind of like a scattering process, right? That's the point. So 2D conform, what is 2D conformal scattering? It's not an S matrix, it's not like this process, it's just 2 points in this space colliding. Okay, that's like the analog of 2 particles colliding. Okay, If you don't get the other technical detail that we only have to look at 3-point functions, that's fine. That's a more technical detail, but trust me when I say we only need to look at 3-point functions, and from 3-point functions, we can build up all higher functions. So this is just some other, like W and W bar I've defined as the same as Z and Z bar, just a different coordinate. And this is going to equal now the sum over K, we'll say, of something called Cij K Z minus W, so now this is the difference in the distances, Z bar minus W bar. Okay, now this is a function of as those points come together, OK of WW bar. Okay, this is the operator product expansion. This is the most important equation we will learn in CFT. And the name of the game, guys, you want to know all the dynamics. First of all, the beauty is you only need a 3-point function. Going to higher points is not really useful. Also, if you look at the little draft of the calculation I sent you, you'll see these kinds of expressions everywhere. This is exactly the kind of expressions we were working with. So it's kind of, now I'm sort of showing you it. Let me write this in a more, I'm going to explain this in more detail. First, let me write this in a nicer way. So we can write this. This is just basically a correlation function. This will be implicit. This is a correlation function. That's what I want to show you that. And I could have a bunch of operators. So we'll put dots there. Right? And then just the same thing. Sum over K, Cij K, C minus W, C bar minus W bar, O of W. Dot. Okay. So this is the set of functions. C is the set of functions dependent on all of this funny business happening when these two things collide. So basically the point, the name of the game, you need to figure out C. C is the constraint. C defines the whole structure of this OPE. That's the name of the game in conformal field theory. We're going to get into more specifics on the structure, but and if we have Bose-Einstein statistics, so these are bosonic operators, then we know that these guys commute. And if we have Fermi-Dirac statistics, right, we know that they just pick up a sign. So OI, OJ in fermion, for fermions, will equal minus OJ, OI. Okay, so we have to be careful if we're doing fermion fields. Right now, we're just talking about scalars. The other O's are totally arbitrary, okay? We don't care. That's the good part about this. We just want to know what's going on at this point. And, you know, we have a singularity as Z approaches W, which will come into the structure of the OP. But the analytic structure is very simple. There's one pole, there's one singularity. It's not very complicated. Okay, I want to end today. So this is the big idea. We're going to spend some time talking about this in the coming weeks after I show you QCD and gauge theory, non-abelian gauge theory, and the beta function. I'm going to talk in more detail about this object. This is kind of a very important thing that we calculate. It's fine if you don't really get all of it yet. Do some more reading about it. Okay. Okay, Polchinski has something in his book. That's good. Okay, let's derive. I want to end today with a simple calculation deriving a ward identity for these operators. Sort of showing the relationship between these correlation functions. So that's what I want to end today with. Let's derive a conformal ward identity. that maintains conformal symmetry. Okay. So let's derive a word identity. So let's start off with some functional integral. We'll call it z equals capital D phi. So I'm going to write down now a functional integral. E to the minus s of phi. Hopefully, I hope this expression is familiar. It better be, or otherwise go do some reading. Okay, let's have phi prime equal phi now plus some epsilon delta phi. So I'm going to vary phi. And of course, I want the action to be invariant. So s of phi prime equals s of phi. Okay, let's put in all of our nice little expressions for conserved currents and so on. And let's derive a word identity. Okay, so now z goes to the integral d sigma prime no, sorry, d phi prime. Why d sigma? Now we're working with phi. Some point described here. exp minus s of phi prime, right? That's just the action. Now let's vary this guy. So that now this is just the integral again, d phi exp. So I don't have to write everything in the exponent. Minus s of phi minus integral. Oh, do I need? Yeah, I need some normalization. Sorry, need some normalization here. 1 over 2 pi integral. Sorry. J alpha delta alpha epsilon, or del alpha epsilon, sorry. Okay, and this just equals the integral phi e to the minus s of phi are functional. One minus 1 over 2 pi integral j alpha delta alpha epsilon. I don't know why I put so many parentheses there. So let me. Okay, where this integral really substitute for d2 sigma square root of g, right? We need all of those factors there. And just be careful. Okay, now we know that the integral of d phi, we know that the integral of d phi e to the minus s phi integral j alpha del alpha epsilon must be 0, just from our basic variational principle. And so now we have that, again, nothing crazy, del alpha j alpha equals 0. And so what this means is now we can derive, so now we basically derived some word identity. So I'll write it down. You'll see how this follows exactly from this expression. So again, this is just phi e. And so now I can write down a word identity from all of this. Okay, then I'll tell you what this means. So minus 1 over 2 pi. So this is the word identity, just from this basic variational technique. Integral over epsilon. Delta alpha J alpha. Sigma O1 of sigma dot dot dot. Equals delta O1 dot dot dot. Okay, what does all this mean? Let's talk about it. Let's talk about what we just did. So basically, all I'm saying now, I do the variational principle. I get some conserved current J alpha del alpha equals 0. All fine and dandy. Now I'm saying that I can, if I have that del alpha J alpha, forget about the epsilon. I have that delta alpha J alpha acting on a string of operators, right? Sorry. That delta alpha J alpha itself is some variation on the string of operators. So in other words, delta alpha J alpha equals this delta. It's just a symmetry transformation. Okay, it's just some conserved thing. I can keep acting on each operator. So this is not really like the direct analog of the word identity in quantum field theory, right? The word identity in quantum field theory is I would say it's a stronger thing because the word identity in quantum field theory, and I say that with caution. I bet someone's going to call me out on that, but I would say that with caution because I think the word identity in quantum field theory is a stronger thing because it interrelates scattering amplitudes. The word identity in conformal field theory simply interrelates correlation functions. And the way it interrelates correlation functions is it says you can keep acting this symmetry on any string of operators and leave it in, and that will leave it invariant. I don't think that's as strong of a statement because in conformal field theory, as we are seeing, the beauty of it in its simplicity, once you solve for C, once you solve for the constraint, you've solved for it. You've solved for all orders of the OPE. The thing is that solving for C depends on the symmetry, depends on delta. Now, in this case, delta is just del alpha J alpha. Delta is just the conserved current or the translational symmetry. It's just a very simple symmetry. I'm saying that, in effect, I'm saying that delta equals del alpha J alpha. However, the symmetry could be very complex, and therefore then determining C in the OPE becomes a challenge. You might use a soft theorem symmetry, which is what we're doing now. The special symmetry is called the sub-subleading soft graviton theorem. Now, you might be asking the following question intuitively, which would be a good one. You might be saying, Kyle, how the heck are we going to relate this to scattering amplitudes? Because this is a very kind of artificial construction at some level. Right? What we've done is we've demanded some exotic symmetry, conformal symmetry, in the hopes that it will lead to some nice description of quantum field theory. Okay, now if you're asking that question, you're very smart because that's the question everyone's trying to answer right now in high energy theory. Not everyone, some people are trying to answer. An aspect of research I'm working on. Can we take the language of S matrices and scattering amplitudes and recast it in conformal field theory? And if so, does that give us any new insight, in particular into quantum gravity? So this question is being worked on. Right now, we have pieces of the puzzle, but we don't see any clear path to a correspondence. You want to know the crazy thing? So people have found a correspondence in anti-de Sitter space. So Juan Maldacena wrote a very famous paper that answers this question I'm telling you, that relates conformal field theories to standard quantum field theory, however, in the topology of anti-de Sitter space. If you want to look this up on Google, this is the very famous ADS CFT correspondence. Okay, so people have done this, and now we're trying to do this for flat space, our topology. The more technical way to say it is we're trying to do it for asymptotically flat space. The even more technical way to say this, which you guys will understand, we're trying to figure out what happens at future and past null infinity, at scri plus minus and scri minus plus. That's the question now. Okay, so if you're saying, okay, now we have all of this fancy stuff, now, okay, but how does this come up in standard QFT? You're absolutely right. That's a question. But the takeaway is to figure out the OPE, you figure out C. We'll talk more about this, obviously. And we have a nice word identity that relates correlation functions. The reason I say I believe it's weaker than the word identity for quantum field theory is in quantum field theory, you have a variety of scattering amplitudes that become interrelated. Whereas in CFT, we're dealing with one singular OPE. Okay, hopefully that was a nice little brief introduction. Obviously, haven't done much. We just kind of recast certain things, done a few little calculations. I'm going to take a detour. Next week, I'm going to, as I said, do non-abelian gauge theory and the beta functions. I think we need a formal discussion of that because I think people are a little confused on some aspects of it. Okay, let me stop recording.